Something is happening at the edge of our solar system, and the people who discovered it are still struggling to explain it. A world that was stripped of its planet status, dismissed as a frozen relic, declared scientifically uninteresting, and essentially abandoned by mainstream astronomy, that world just forced the most powerful space telescope ever built to stare at it in disbelief. What James Webb found when it finally pointed its golden mirror at Pluto was not what anyone expected. It was not what the models predicted. It was not what the textbooks described. And here is the part nobody is talking about. What Webb found on Pluto might actually be a mirror of what Earth looked like 2.4 billion years ago. There is a moment in every great scientific story where the instrument does not just confirm what scientists suspected, it shatters the assumption entirely. That moment happened with Pluto, and it happened not once, but repeatedly, across a series of observations conducted between 2022 and 2023, the results of which began cascading into the scientific literature in early 2025 and continued through June of that same year, published in two of the most respected journals on the planet, Astronomy and Astrophysics and Nature Astronomy. What those papers described was not a minor update to our understanding of a distant dwarf planet. What they described was a complete reclassification of what kind of world Pluto actually is. To understand why this is so significant, you have to go back to 2006. That was the year the International Astronomical Union, in one of the most controversial decisions in the history of modern science, voted to strip Pluto of its planetary status. For 76 years, Pluto had been the 9th planet. Children grew up memorizing its name, textbooks included it, and then, in a single vote, it was reclassified as a dwarf planet. The scientific community argued it had not cleared its orbital neighborhood, a technical criterion that, to many astronomers, felt like moving the goalposts. But beyond the politics of classification, the deeper message sent to the public was this: Pluto is small, it is cold, it is boring, and it is not worth our full attention anymore. That message, as it turns out, was catastrophically wrong. Then came New Horizons. NASA's remarkable spacecraft, launched in 2006 and arriving at Pluto in July 2015 after a journey of nearly 5 billion kilometers, changed everything in a single flyby. What New Horizons revealed was a world of staggering complexity. There were mountain ranges made of water ice, rising 3 kilometers above the surface. There were vast nitrogen glaciers slowly moving across plains. There was a heart-shaped feature the size of Texas, a region now called Tomball Regio, that appeared to be geologically active in ways that defied expectation, and floating above all of it, extending more than 300 kilometers above the surface, was a layered blue haze, a haze that no one had fully accounted for, a haze that the models did not predict with any real accuracy. Scientists looked at this haze and they knew, immediately, that something unusual was happening in Pluto's atmosphere. But they did not yet have the tools to understand exactly what. That understanding would have to wait nearly a decade, and this is where everything changes. In 2017, a planetary scientist at the University of California, Santa Cruz named Xi Zhang published a paper that, by his own admission, contained what he called a crazy idea. Zhang had been studying the data from New Horizons and working through the numbers on Pluto's atmospheric energy balance. What he found was troubling. The gas in Pluto's atmosphere was being heated by solar radiation. That much was consistent with expectations. But the amount of heating significantly exceeded the cooling that could be explained by the gas alone. Something else had to be providing the cooling. Something had to be absorbing energy and then radiating it away in a form that kept Pluto's upper atmosphere from becoming far warmer than it actually was. Zhang's hypothesis was radical. The haze itself, those tiny particles of organic material floating high above Pluto's surface, was acting as the atmosphere's primary thermostat. The haze was heating up, absorbing solar radiation and then emitting it as infrared radiation, effectively cooling the gas around it. If this was true, it would mean Pluto had a climate system unlike anything else in the solar system. A climate system not controlled by gas dynamics, not controlled by surface albedo, not controlled by any of the mechanisms that drive weather on every other world we know, but controlled by particles. Tiny, complex, chemically rich particles floating in the dark. The scientific community was skeptical. The idea was bold, even provocative, and it came with a prediction that could be tested, but only by an instrument sensitive enough to detect the faint mid-infrared emissions from a world nearly 4 billion miles away. In 2017, no such instrument existed. But in December 2021, humanity launched one. The James Webb Space Telescope is not just a bigger version of Hubble. That framing fundamentally undersells what Webb actually is. Webb operates primarily in the infrared spectrum, capturing wavelengths of light that carry heat signatures, chemical fingerprints, and atmospheric data that are completely invisible to optical telescopes. Its primary mirror spans 6.5 meters. nearly 3 times the diameter of Hubble's. It sits at a point in space called L2, 1.5 million kilometers from Earth, where it can maintain the extreme cold necessary for its instruments to function. Its sunshield is the size of a tennis court and provides protection equivalent to an SPF factor of 1 million. And critically, one of its instruments, the mid-infrared instrument known as MIRI, was designed to operate in exactly the spectral range that Xi Zhang's 2017 prediction required. The telescope that could finally test the crazy idea had arrived. And in 2022, scientists pointed it at Pluto. Think about what that means for a moment. For the first time in history, humanity had an instrument sensitive enough to take the thermal temperature of a world nearly 4 billion miles away, and separate the heat signature of that world from its moon, and detect the faint infrared glow of atmospheric haze particles floating 300 kilometers above an icy surface in the outer darkness of the solar system. That is not just impressive engineering. That is a new category of human perception. We developed a sense that evolution never gave us, aimed it at the edge of everything we can reach, and listened. What MIRI heard was extraordinary. The observations were conducted in 2 phases. In 2022, the MIRI imager captured what are called light curves, measurements of the thermal radiation emitted by Pluto and Charon at 4 specific wavelengths, 15, 18, 21, and 25 micrometers. These measurements were taken as Pluto and Charon rotated, which meant the data captured thermal variations across different parts of their surfaces. For Pluto, these variations were sensitive to the surface properties of different terrains, regions covered in methane ice, water ice, and darker organic deposits, each radiating heat at slightly different rates. For Charon, the data revealed dramatic differences between regions covered in pure water ice and the dark reddish polar regions, where methane molecules captured from Pluto's own escaping atmosphere had been chemically transformed over millions of years. This was already remarkable. For the first time, researchers could map the thermal landscape of Pluto and Charon simultaneously, distinguishing not just their surfaces from one another, but the different material compositions within each world. But the 2022 data was only the beginning. In May 2023, the MIRI instrument captured something even more significant. Scientists directed Webb to take a high-quality mid-infrared spectrum of Pluto's atmosphere across a spectral range spanning from 4.9 to 27 micrometers. This range had never been explored for Pluto before. Previous instruments, including those on New Horizons, simply did not have the sensitivity to detect the faint signals coming from Pluto's thin atmosphere at these wavelengths, but MIRI could. And what the spectrum revealed was described by researchers as unexpected chemical richness. The atmosphere of Pluto, already known to contain nitrogen, methane, and carbon monoxide, was shown to have a far more complex chemical inventory than anyone had mapped in the spectral regime. Signatures of methane ice, deuterated methane, and ethylene were detected in the reflected solar component of the spectrum. And most critically, the haze itself, those particles that Xi Zhang had hypothesized were controlling Pluto's energy balance, was clearly visible as a distinct thermal source, emitting its own infrared signature with features appearing at multiple wavelengths across the mid-infrared range. The haze was real, the haze was radiating, and the haze was doing exactly what the crazy idea predicted. Here is what the data actually showed about how this works. High in Pluto's atmosphere, far above the surface, the sun's ultraviolet radiation strikes molecules of nitrogen and methane. These molecules are ionized and broken apart, and they begin reacting with one another to form complex hydrocarbon particles. Tiny structures just tens of nanometers in diameter, far smaller than anything visible to the naked eye. These particles accumulate high in the atmosphere, absorbing incoming solar radiation and then emitting that energy back out as infrared light. As they do so, they cool the gas surrounding them. Then, slowly, gravity pulls the particles downward. As they descend, they collide with other particles and aggregate, growing larger as they fall, eventually settling onto Pluto's icy surface. This process is continuous. The sun is constantly driving new chemistry in the upper atmosphere, constantly producing new particles, constantly refreshing the haze layer, and the haze layer is constantly cooling the atmosphere from within. This is not a passive, dormant chemical process. This is a dynamic, self-regulating climate engine, running on photochemistry and particle physics at the edge of the solar system. But here's where it gets worse, or rather, where it gets more strange, more layered, more consequential. This climate system is not isolated. It is not contained within Pluto alone. The haze particles that fall to the surface are depositing complex organic chemistry directly onto Pluto's ice. They are building up layers of hydrocarbon material that alter the optical and thermal properties of the surface over time. And the atmosphere itself, driven by this haze, is directly connected to Pluto's neighbor. Pluto's moon Charon orbits so close, just under 20,000 kilometers away, that Pluto's escaping atmosphere physically reaches it. Methane molecules leaking from Pluto's atmosphere at a rate of approximately 1.4 kilograms per second, according to data from New Horizons, travel across the void between the two worlds and are captured by Charon's gravity. At Charon's poles, where temperatures are coldest, these molecules freeze and then undergo chemical transformation under ultraviolet radiation, producing the reddish organic compounds that color Charon's north and south poles. The JWST data confirm this process with a precision that earlier observations simply could not achieve. What you are looking at when you study the Pluto-Charon system through Webb's eyes is a world actively exhaling, and its neighbor breathing in. This interaction, as the researchers pointed out in their published papers, is unique in the solar system. There is no other known pair of worlds where one world's atmosphere is actively and continuously depositing material on another. Earth has no such relationship with the moon. Mars has no such relationship with Phobos. Saturn's moons interact, gravitationally but not atmospherically in this direct particle-by-particle manner. Pluto and Charon are, as one team described it, a system unto themselves, a small, cold, chemically linked binary world at the edge of the solar system, where the boundary between one world and another is not a hard line, but a gradient of escaping gases and drifting particles. And now consider where this takes us scientifically, because the implications extend far beyond Pluto. Xizheng made a comment in the wake of these confirmations that deserves to be read carefully. He noted that before oxygen built up in Earth's atmosphere, approximately 2.4 billion years ago, our planet's atmosphere was composed primarily of nitrogen and hydrocarbons, exactly the same chemical mixture that dominates Pluto's atmosphere. Today, life already existed on Earth during that period, thriving under conditions with no free oxygen, in an atmosphere rich with the same kind of photochemical haze that now blankets Pluto. What this means is that Pluto is not an alien world in the way we typically use that phrase. It is a time capsule. It is a working, real-time laboratory running a chemistry experiment that Earth itself ran billions of years ago and then abandoned when photosynthesis changed everything. By studying Pluto's haze, its composition, its behavior, its thermal dynamics, scientists may be able to reconstruct what Earth's early atmosphere actually looked like in practice, not just in theoretical models. They may be able to understand the chemical conditions under which the first forms of life on this planet arose. Read that again. Pluto, the world we demoted, the world we dismissed, the world we spent decades treating as an afterthought, may hold the chemical key to understanding the origin of life on Earth. But the story does not stop there. Because what JWST revealed about Pluto's relationship with Titan, Saturn's largest moon, is equally stunning. Scientists have recently found that the same mystery chemical fingerprint detected in Titan's thick orange atmosphere has also been identified on Pluto. Both atmospheres are dominated by nitrogen and methane. Both produce haze through the same photochemical processes. And now both show the same spectral signature in infrared observations. Titan has long been considered one of the most Earth-like bodies in the solar system, not because of its temperature or its distance from the sun, but because of its complex organic chemistry and its thick nitrogen atmosphere. The fact that Pluto shares this chemistry in a dramatically different environment, 3.7 billion miles from the sun, suggests that nitrogen-methane photochemistry is not an exotic edge case. It may be one of the most common chemical processes in the outer solar system, one that occurs wherever nitrogen and methane are present, and sunlight, however faint, can drive reactions. What most people are not seeing is this. We are beginning to understand that the outer solar system is not a cold, inert wasteland. It is a chemically active frontier, where complex organic molecules are being produced continuously, where atmospheres are being shaped by forces we are only beginning to understand, and where the boundary conditions for what we consider a living chemistry may be far broader than our Earth-centric models have ever allowed. The JWST data also forced researchers to revise their thermal models of Pluto's surface in ways that have practical implications for future mission planning. The light curves captured by MIRI revealed that Pluto's surface is far more thermally varied than previous models suggested. Different regions have different thermal inertia, the rate at which they absorb and release heat. Methane ice regions, water ice regions, and dark organic deposit regions all behave differently. These differences are what drive the redistribution of volatile ices across Pluto's surface over the course of its highly elliptical 248-year orbit. Pluto's orbit is so elongated that at perihelion, its closest point to the Sun, it is closer than Neptune. At aphelion, it retreats to nearly 50 astronomical units. As it moves along this orbit, the balance of sunlight changes dramatically, causing ices to sublimate in some regions and condense in others. The new thermal data from JWST gives scientists the most accurate map ever produced of how this redistribution actually happens, and the results are far more dynamic than expected. Pluto, even in the cold outer darkness of the Kuiper Belt, is not frozen in place. It is actively reshaping its own surface over timescales of decades and centuries. And here's the detail that truly stands out against everything else. The haze that controls Pluto's climate is not stable. It rises and falls. It changes. JWST watched it happen. The particles in Pluto's atmosphere heat during certain periods and cool during others, causing the haze to expand and contract, rising higher above the surface at sometimes and descending closer at others. This is not a static veil. This is a breathing system, a thermal engine that pulses. And the fact that Webb could detect this pulsing from 3.7 billion miles away in a wavelength regime that had never been explored for Pluto before tells you something profound about both the instrument and the world it was watching. According to the researchers who led these studies, including Tanguy Bertrand of the Observatoire de Paris, who led the primary analysis team, and Xi Zhang of UC Santa Cruz, whose 2017 prediction was ultimately confirmed, the agreement between what the models predicted and what JWST actually, kind of scientific alignment that gives researchers confidence not just in the specific results, but in the underlying physical understanding that generated those results. But what does this mean for what comes next? The JWST observations of Pluto are not complete. Researchers are already planning follow-up observations. They want to track Pluto across multiple rotations to better characterize how the haze varies not just as a function of surface terrain, but as a function of time. They want to fill in spectral gaps in the current data that may reveal additional chemical species. And they want to use Pluto as a template for studying other trans-Neptunian objects, the icy worlds that populate the Kuiper Belt beyond Neptune, most of which have never been observed with anywhere near the resolution or spectral detail that Webb has now delivered for Pluto. There are hundreds of these objects, possibly thousands, that we have not yet discovered. And if the chemistry operating on Pluto is representative of the broader Kuiper Belt population, then what we are discovering is not just a new understanding of one dwarf planet. We are beginning to understand an entire class of worlds that orbit the outer solar system in the dark, manufacturing complex organic chemistry in ways that challenge our fundamental assumptions about where life-relevant molecules can form. There's also the question of a mission. For years, scientists have been advocating for a dedicated follow-up mission to Pluto, one that would not just fly past, as New Horizons did, but actually orbit the dwarf planet and study it systematically over time. The New Horizons flyby lasted only a matter of hours at closest approach. A full orbital mission would allow scientists to map Pluto across its seasons, track the changes in its atmosphere, measure the rate of volatile ice migration across its surface, and potentially even search for evidence of a subsurface ocean, a possibility that has been raised by some researchers based on the thermal data and Pluto's unusual geological activity. The JWST findings have added new urgency to this conversation. What Webb has revealed is not a simplified picture that answers our questions about Pluto. It is a more complex picture that generates new questions, and those questions demand a closer look. What most people are still not grasping is the full scale of what has changed. For most of the 20th century and into the 21st, Pluto was treated as a footnote, a curiosity, a failed planet that was too small, too cold, too far, and too insignificant to warrant serious long-term investment. So this New Horizons flyby cracked that assumption. But even after New Horizons, Pluto remained at the margins of planetary science, not because the data wasn't compelling, but because the instruments available were not sensitive enough to go deeper. Webb changed that. Webb gave scientists, for the first time, the ability to study Pluto's atmosphere in the mid-infrared, a spectral window that carries more information about atmospheric chemistry and thermal dynamics than any other wavelength range that had previously been accessible. And what was found in that window was not a simple confirmation of existing models, it was a revelation about the nature of the world itself. The real story is this: Pluto is alive in ways that no one fully appreciated before 2015, and in ways that even the revelations of New Horizons did not fully capture. Its atmosphere is not a passive byproduct of surface ice sublimation. It is an active, self-regulating system in which photochemistry, particle dynamics, and thermal radiation interact to produce a climate unlike anything else in the solar system. Its haze is not decorative, it is functional. It is the thermostat, the chemistry lab, and the delivery system, all at once, driving processes that extend from the upper atmosphere all the way to the surface of its neighboring moon. And the chemistry it is producing, the organic compounds raining down from its sky, may be directly analogous to the chemistry that was present on early Earth, when the first living things began to emerge. We spent decades looking past Pluto. We stripped it of its title. We sent one spacecraft for one brief encounter and called it enough. And all the while, 3.7 billion miles away, this small, cold, complex world was running an atmospheric experiment that echoes across billions of years of planetary and biological history. It was doing things that our models said it shouldn't be able to do, maintaining a climate engine powered by particles smaller than a wavelength of visible light, feeding chemistry to its moon across open space, preserving in its atmospheric haze a chemical record that may tell us more about the origin of life on Earth than any experiment we have run in a laboratory. What James Webb did when it pointed at Pluto was not just observe a distant world. It opened a door that we thought was closed, and what is on the other side of that door is still being mapped. The papers published in 2025 are the beginning, not the conclusion. The spectral gaps that remain in the current data are not empty spaces. They are invitations. They are regions of the infrared. Spectrum where JWST has not yet looked, where new molecules may be waiting to be identified, where the chemical inventory of Pluto's atmosphere may turn out to be even richer than what has already been found. And beyond Pluto, in the deep cold of the Kuiper Belt, hundreds of other worlds are waiting, each one potentially running its own version of the same chemistry, each one a data point in a larger pattern that we are only just beginning to trace. The question that no one is asking loudly enough is this: if Pluto, a world we dismissed and demoted, turned out to be this scientifically consequential, what else is out there that we have been too quick to ignore? What other worlds, too cold, too small, too far from the center of our attention, are doing things that our models say should not be? Possible? The outer solar system is vast. The Kuiper Belt alone contains more material by count than the inner solar system. And our instruments, until Webb, simply could not reach it at the spectral depth required to understand what was actually happening out there. Now they can, and what they are finding is that the darkness at the edge of our solar system is not empty. It is not silent. It is not dead. It is a place where the chemistry of life's origin is still running, slowly, patiently, in a world that lost its planet status, but never. Something bigger is coming from the Kuiper Belt. The data has only just begun to arrive.